The universe began in a state of perfect simplicity. For nearly 1 billion years, it was a realm of profound darkness and silent transformation, a chapter written in invisible ink. This is the story of the first billion years after the Big Bang, a mystery of cosmic origins. By the end, you will understand how our entire structured universe emerged from an almost featureless fog. How did a hot, uniform sea of particles give birth to the very first stars and galaxies? We are about to trace the journey from the Big Bang's fading afterglow to the dawn of the first cosmic structures, a frontier pieced together by theory and incredible observation. What do you think it took to build a universe from nothing but potential that perfect simplicity could not last? A profound change was already underway, one that would freeze a single, universal moment into a permanent cosmic photograph. This is the event we call recombination, occurring roughly 380,000 years after the Big Bang. Until this point, the universe was an opaque, searing plasma, a thick soup where protons and electrons, all positively and negatively charged, were constantly scattering light. Photons could not travel freely, they were trapped in a chaotic dance with matter, but as the cosmos expanded, it cooled, and when it cooled to a temperature of about 3000 Kelvin, something remarkable happened. Protons and electrons finally slowed down enough to combine and form the first stable atoms of neutral hydrogen with a dash of helium. Think of it as the universe suddenly clearing its throat. The charged particles were now bound into neutral atoms, and light, for the very first time, was set free. That initial flash of liberated light is what we detect today as the cosmic microwave background radiation. It is the oldest light in existence, a baby picture of the universe, showing us its state at that exact moment. But what did that picture reveal? The universe at 380,000 years old was now transparent, but it was utterly and completely dark. No stars, no galaxies, not a single source of illumination. It was a vast, quiet sea of hydrogen and helium gas, almost perfectly smooth. Almost, the cosmic microwave background is not a featureless glow. It has tiny, whisper question variations in temperature. These are the imprints of those infinitesimal density fluctuations from the inflationary epoch, quantum ripples stretched to cosmic scales. In some regions, the gas was ever so slightly denser, a few more atoms per cubic mile than in others. This was the universe's entire blueprint, the only raw material it had to work with. All the grandeur to come, every galaxy cluster, every spiral arm, every star and planet, was encoded in those faint imperfections within the dark. Gravity now had something to pull on, and the long, patient work of building a cosmos was ready to begin. That ancient light, now free to travel, began a journey across an expanding emptiness. With the birth of atoms, the universe entered its longest and most silent chapter, a span of profound stillness known as the Cosmic Dark Ages. This era lasted for several 100 million years, a stretch of time so vast it makes all of human history seem like a single breath. And the name is perfectly literal, for there were no stars, no galaxies, not a single candle to pierce the endless night. The cosmos was a truly dark place, filled only with that cooling sea of neutral hydrogen and helium gas. Yet in the darkness, an invisible architecture was already taking shape. While the ordinary matter, the gas, was still smoothly spread, a mysterious component called dark matter had a head start. Dark matter, which does not interact with light at all, had already begun responding to the gravitational pull of those tiny density ripples from the early universe. It was slowly, inexorably clumping together, weaving itself into a vast and intricate cosmic web of filaments and immense, shadowy halos. Think of this web as the universe's unseen skeleton, a gravitational blueprint laid down in the dark. The neutral hydrogen gas, meanwhile, simply flowed along, soon to be drawn into the gravitational wells that dark matter was preparing. This makes the Dark Ages a paradox, one of the least observable periods in cosmic history, yet arguably the most critical. Our telescopes, which rely on light, struggle to see this era directly, for there was no light to see. It is a blank page in our cosmic storybook, yet on this page the fate of everything was being decided in silence. Yet within that almost perfect smoothness, the faintest of whispers held the entire future. Those tiny temperature differences we see in the cosmic microwave background are not just random noise. They are the literal seeds of every galaxy, star, and planet that would ever exist. Their origin is one of the most profound ideas in all of cosmology, a direct link between the impossibly small world of quantum mechanics and the vast structure of our universe. In the first fleeting fraction of a second after the Big Bang, during the period of hyper-fast expansion called inflation, the fabric of space-time itself was a turbulent quantum foam. At this scale, empty space is not empty. It seethes with temporary particles and energy popping in and out of existence. These are quantum fluctuations, brief irregularities in energy that are normally too small to matter. But inflation stretched these tiny quantum ripples in space-time itself, magnifying them to staggering cosmic proportions. Imagine blowing up a microscopic wrinkle on a balloon's surface until it becomes a continent-sized feature. That is what inflation did. These stretched ripples became permanent variations in the density of the universe, regions where the primordial plasma was ever so slightly denser or thinner than the average. They are the primordial density fluctuations, the universe's original blueprint. The cosmic microwave background is our direct snapshot of this blueprint, frozen in time. Each slightly warmer patch in that ancient light corresponds to a region of slightly higher density, a place where gravity had just a little more to work with. And here is where the story splits in two. Ordinary matter, the protons and electrons, was still coupled to the intense radiation pressure of the early universe, like a leaf caught in a hurricane. It could not yet collapse under its own gravity. But dark matter, mysterious and invisible, feels gravity alone. Unaffected by that raging radiation, dark matter particles began to respond to the pull of these overdensities first. They started to drift ever so slowly into the denser regions, creating the first gravitational wells in the darkness. These wells, sculpted by dark matter, would become the invisible molds into which all the visible universe would eventually flow. So when we look at that map of the infant cosmos, we are not just seeing a pretty pattern of hot and cold. We are staring at the birth certificate of cosmic structure itself, signed by the quantum laws of the very small. While the visible universe remained a featureless dark sea, an invisible architecture was already rising. This is the era when dark matter, specifically what we call cold dark matter, began its quiet, dominant work. Its defining characteristic, that it only interacts through gravity, was its ultimate advantage. Unlike ordinary matter, the protons and electrons that were still buffeted by the intense pressure of radiation, dark matter felt only the gentle, persistent tug of gravity. It was free to respond to the faint gravitational whispers of those primordial density ripples. Think of it like this: in a crowded, noisy room, ordinary matter is trying to have a conversation but is constantly being jostled by the crowd. Dark matter is in a soundproof booth, able to focus solely on the single voice of gravity. So it began to move, slowly drifting toward the slightly denser regions mapped out by the cosmic microwave background. Over millions of years, this drift created the first true structures in the cosmos, not made of stars or gas, but of pure, invisible mass. These structures formed a vast, three-dimensional web, a cosmic skeleton. At the intersections of this web, dark matter piled up into immense, roughly spherical clouds called halos. Vast filaments of dark matter connected these dense nodes, stretching across the emptiness like the strands of a spiderweb drenched in morning dew. This dark matter scaffolding became the universe's gravitational blueprint. The halos are not the galaxies themselves. They are the deep gravitational wells, the invisible molds, into which the neutral hydrogen gas will eventually flow, cool, and collapse to spark the first stars. Every majestic galaxy we see today, from great spirals to giant ellipticals, resides at the heart of one of these ancient dark matter halos. The hierarchy of cosmic structure was set, not by the brilliant stuff we see, but by the silent, unseen majority that shaped the stage long before the actors arrived. The silent web of dark matter was not a static sculpture. Gravity is a patient but relentless force, and within the densest knots of that cosmic skeleton, a profound shift was beginning. While the universe as a whole continued its relentless expansion, carried outward by the momentum of the Big Bang, specific regions began to fall out of that universal flow. These were the places where dark matter had gathered most thickly, creating gravitational wells so deep that the local pull of their own mass overcame the outward rush of space itself. Think of a fast-moving river where a deep, still eddy forms behind a large rock. The river keeps flowing, but within that eddy, the water turns back on itself, swirling in a separate dance. That is what happened cosmically. A region of slightly higher density, once just a faint ripple in the early universe, stopped expanding with everything else. It reached a point of maximum size, hesitated, and then began to collapse inward under its own weight. This was the birth of the first true structures, the dark matter minihalos. Their name hints at their scale, for in cosmic terms they were remarkably small, perhaps only a few 100,000 times the mass of our Sun. To a modern galaxy, which can be trillions of solar masses, these were mere seeds. But they were the crucial first step. Within the secure gravitational embrace of these minihalos, the neutral hydrogen gas that had been flowing along with the dark matter finally found a home. The gas, now gathered into these deepening wells, began to behave differently. As it became denser, atoms collided more frequently. These collisions allowed the gas to do something essential. It could release energy in the form of faint radiation and cool down. Cooling is the secret ingredient for star formation. A hot gas cloud has too much internal pressure. It puffs itself up and resists collapse. But as this primordial hydrogen cooled, its pressure dropped. Without that supporting pressure, the relentless pull of gravity from the surrounding dark matter halo became irresistible. Vast, swirling pools of gas began to condense at the hearts of these minihalos, growing denser and denser. They were not yet stars and not quite galaxies. They were the first protogalaxies, dark, gaseous nurseries waiting for a spark. Within their deepest, densest cores, conditions were becoming extreme, setting the stage for an event that would forever end the cosmic dark ages, the ignition of the very first starlight. The spark of the first stars was not a simple matter of gravity pulling gas together. There was a profound and beautiful physics puzzle to solve, a cosmic challenge of cooling. To understand why, picture a cloud of gas collapsing under its own weight. As it shrinks, the atoms are squeezed closer together, colliding more frequently. Each collision generates heat, and that heat creates an outward pressure, like air in a bicycle pump getting warmer as you compress it. This thermal pressure fights against the inward pull of gravity. For the collapse to continue all the way to a star, the gas must find a way to lose that energy, to cool down and let gravity win. In our modern universe, this is relatively easy. Interstellar gas clouds are laced with microscopic dust grains and heavier elements, which we call metals in astronomy. These tiny particles are incredibly efficient at radiating heat away into space, allowing vast clouds to cool and fragment into many stars. But in the pristine early universe, there were no metals, no dust. The gas was pure hydrogen and helium, two of the simplest and most stubborn elements when it comes to cooling. A single hydrogen atom by itself is very bad at releasing energy. So how did the first protostars overcome this? The universe found an elegant, fragile solution: molecular hydrogen. Deep within those swirling pools of gas at the hearts of dark matter minihalos, a special chemical process began. Amidst the sea of single hydrogen atoms, trace amounts of molecular hydrogen, or H2, started to form. This molecule, simply two hydrogen atoms bound together, has a special property. It can vibrate and rotate in ways that a single atom cannot, and these motions allow it to emit faint infrared radiation, effectively shedding heat. Creating this crucial coolant, however, was a delicate dance. It required a three-body reaction where two hydrogen atoms could not simply meet and bond. They needed a third partner to help carry away the excess energy of the union. That partner was often a free electron. An electron would briefly attach to a hydrogen atom, forming a negative ion, which could then attract a second hydrogen atom. When the electron departed, it took the extra energy with it, leaving behind a stable H2 molecule. It was a slow, inefficient process, but in the dense cores of these collapsing clouds, it was just enough. As these first molecules formed, they began to act as a cosmic radiator. The gravitational energy of the collapse was converted into molecular vibrations, which were then radiated away as infrared light, escaping into the void. This molecular hydrogen cooling was the secret key that unlocked star formation. It allowed the densest clumps of gas within the minihalos to continue their inward fall, shedding heat so gravity could keep tightening its grip. Without this fragile molecular coolant, the gas would have simply heated up until it stabilized, a warm, puffed-up cloud forever on the brink of greatness. But with it, the core temperatures and densities soared, setting the stage for a nuclear fire that would change everything. These first stellar nurseries gave birth to a generation of stars unlike any we have ever seen. Astronomers call them Population 3 stars, the true pioneers of the cosmos. To understand just how unique they were, we need to look at the stellar family tree. Our own Sun is a Population 1 star, rich in heavier elements we call metals, born from gas that had been recycled through many generations of stellar lives and deaths. Older stars in the halo of our galaxy are Population 2, containing far fewer metals, but Population 3 stars were the original, formed from the pure, untainted hydrogen and helium gas of the early universe. They contained not a single atom of carbon, oxygen, iron, or any element heavier than helium. This pristine composition made them fundamentally alien. Without metals, their internal physics worked differently. Metals are fantastic at cooling gas, allowing modern clouds to fragment into many small stars. But in that pure gas, cooling was so inefficient that only enormous clumps of material could collapse. This is why theorists believe Population 3 stars were behemoths, likely weighing in at tens or even hundreds of times the mass of our Sun. Imagine a star not as a distant twinkle, but as a colossal furnace that could outshine a small modern galaxy. Their immense mass meant crushing gravity at their cores, driving temperatures and pressures to staggering extremes. They burned their nuclear fuel with a ferocious blue-white intensity and lived lives of breathtaking brevity. While a star like our Sun will shine for billions of years, a massive Population 3 star might exhaust its entire supply of hydrogen in just a few million years, a cosmic blink of an eye. Their fate was sealed by their own brilliance. This first generation of stars did not simply fade away. They lived fast, died young, and in their spectacular deaths, they performed the universe's most crucial act of alchemy, transforming the simple beginnings into the complex foundations for everything to come. Their spectacular deaths were still millions of years in the future, but their birth was an event of immediate, universe-altering power. deep within the densest core of a collapsing gas cloud, where temperatures soared past 10 million degrees, a new and fundamental force awoke. The immense pressure and heat finally overcame the electrical repulsion between hydrogen nuclei, forcing them to fuse together into helium. In that instant, nuclear fusion ignited in the heart of a primordial cloud, and the first star was born. Its light did not simply turn on, it exploded outward, a shockwave of pure energy. This was not the gentle yellow glow of our sun, but a searing, blistering torrent of ultraviolet radiation. For the first time in nearly 500 million years, something other than the fading cosmic microwave background was illuminating the cosmos. The long, silent cosmic dark ages were over. This first starlight began to flood the space around it, and it did something radical to the quiet universe. That intense ultraviolet radiation slammed into the surrounding sea of neutral hydrogen atoms. Each photon carried enough energy to knock the single electron right off a hydrogen atom, tearing it apart once more into a free proton and a free electron. This process is called reionization. Around that first brilliant beacon, a growing bubble of ionized, glowing gas began to form, what astronomers call an H2 region. Imagine a single lit match in an impossibly vast dark cavern. The flame itself is tiny, but it pushes back the darkness immediately around it, creating a small sphere of flickering light and heat. That is what these first stars did on a cosmic scale. They were lighthouses in a universal sea of neutral fog, each one carving out its own bubble of clear, ionized space. But the cosmos was unimaginably large, and these first stars, though unimaginably bright, were also incredibly rare and isolated. They were scattered like distant campfires across a continent-sized plain. Their individual bubbles of light did not yet touch. The universe remained a patchwork, a vast neutral wilderness punctuated by these brilliant, isolated oases of searing radiation and reionized gas. To truly fill the cosmos with light, these pioneers would need to come together, to gather and build something greater than themselves. The next chapter would be written not by individual stars, but by their collective gravity, drawing them into the first true communities in the darkness. Their brilliant lives were a cosmic sprint, not a marathon. A star hundreds of times more massive than our sun possesses a furnace of unimaginable fury, but it pays a steep price for that power. It burns through its vast reservoir of pristine hydrogen fuel in a mere few million years, a fleeting instant compared to the 10 billion-year lifespan of a star like our own. For these titans, the end was always destined to be dramatic, a final act that would reshape their corner of the cosmos. The fate of each star was written by its precise mass. The very largest of these pioneers, perhaps above 250 solar masses, may have met a uniquely quiet yet profound end. Their own gravity, so immense, could have become unstable at the very core. When their nuclear fuel was exhausted, there may have been no explosive supernova at all. Instead, the entire star would have simply collapsed in on itself, vanishing from sight as it directly formed a black hole, a silent gravitational tomb in the early darkness. But for many other massive first stars, the finale was anything but quiet. Their cores became layered like a cosmic onion, fusing heavier and heavier elements, from helium to carbon, oxygen, and eventually silicon, all the way up to iron. And iron is the end of the line for stellar fusion. Fusing iron does not release energy, it consumes it. In that critical moment, the star's central support system failed. The core catastrophically collapsed in less than a second, then rebounded in a titanic shockwave that blasted the star's outer layers into space at nearly a tenth the speed of light. This was a pair instability supernova, an explosion so utterly complete that it left no remnant behind, scattering every atom of the star far and wide. This is where the story turns from destruction to creation, from an end to a vital new beginning. In the unimaginable heart of that explosion, for fleeting moments, temperatures and pressures exceeded those of the star's entire life. Here, in the fury of the supernova itself, atoms were smashed together to form every natural element heavier than iron, from cobalt and nickel to gold and uranium. Then the explosion acted as a cosmic farmer, seeding the surrounding void. It hurled this newly forged material carbon, oxygen, silicon, iron, and traces of everything else out into the primordial hydrogen and helium gas that filled the minihalo and beyond. This was the first pollution of the universe, and it was an absolute necessity. That enriched gas, now laced with these heavy elements or metals, was forever changed. The next time gravity gathered gas to form a star, it would not be from pure ingredients. It would be from this enriched material, which could cool far more efficiently thanks to those metal atoms. This meant future clouds could fragment into many smaller, longer-lived stars like our Sun. The first stars, through their deaths, fundamentally altered the recipe for all stars to come. But their feedback was not merely chemical. The sheer energy of their explosions sent powerful shock waves rippling through the neighboring gas. These waves could compress other gas clouds, triggering a second wave of star formation in a nearby region. Or conversely, that ferocious energy could blast a cloud apart, dispersing it and delaying any further activity for eons. The first stars were not just luminous objects, they were the universe's first agents of change, their brief lives governing the chemistry and the very rhythm of creation in their wake. They transformed a simple, dark cosmos into one rich with potential, setting the table for everything that was to follow. These brilliant, isolated beacons were not destined to remain alone forever. Gravity, the great architect of the cosmos, was already at work on a grander scale, drawing these first stars and their surrounding gas into the very first true communities. We call these the first galaxies, and they mark a pivotal step in cosmic evolution. But what exactly do we mean by a first galaxy in this ancient context? It is more than just a cluster of stars. A galaxy, even a primordial one, is a gravitationally bound system, a permanent island of matter in the expanding void. It contains not just stars but the gas from which new stars form, all held together within the immense, invisible embrace of a dark matter halo. This is a key distinction. A single, massive population 3-star and its surrounding bubble of ionized gas was a temporary event. A galaxy was a lasting structure, a stable engine for ongoing creation. So how did these first islands assemble? The process was one of cosmic mergers and steady feeding. Picture the dark matter web with its dense nodes and connecting filaments. Those first star-forming minihalos did not form in perfect isolation. They were often neighbors along the same dark matter filament. Their own mutual gravity began to pull them together. Over tens of millions of years, these smaller halos, each perhaps containing a few massive stars or a small cluster, would slowly dance toward one another and merge. It was a gentle collision on a cosmic scale, their dark matter halos blending into one larger halo, their gas clouds sloshing together and triggering new, intense waves of star formation. At the same time, fresh, neutral hydrogen gas continued to stream in from the cosmic web, flowing along those dark matter filaments like water converging into a river delta, constantly feeding the growing structure. The result was a protogalaxy, a foundational building block of the universe we know. By modern standards, it was tiny and misshapen, perhaps only 1% the size and mass of our Milky Way. It would have looked nothing like a majestic spiral or smooth ellipse. These first galaxies were likely irregular blobs of light, turbulent and chaotic, blazing with the fierce blue glow of short-lived massive stars. But their importance cannot be overstated. They were the first permanent settlements of light in the universal dark. Within them, the cycle of star birth, life, and death could begin in earnest, their gas enriched by each generation of supernova, allowing for more and more varied stars to form. They were no longer temporary campfires, but the first established towns, drawing resources from the countryside and growing into the cities that would one day form the great galactic clusters we see today. But these chaotic, brilliant islands of starlight held a secret at their very heart, a hidden engine that would one day outshine them all. While the first stars were forging the elements of life, something else was taking root in the dense cores of the earliest protogalaxies, something that would grow to become the most powerful objects in the universe. We are talking about the seeds of supermassive black holes. Today, we find these cosmic giants, weighing millions or even billions of times the mass of our Sun, sitting at the center of nearly every large galaxy, including our own Milky Way. Their existence poses a profound puzzle. How did they get so big so fast? The universe was not old enough for a typical stellar mass black hole, the kind left behind when a massive star dies, to grow to such monstrous proportions through slow feeding alone. They needed a head start. They needed seeds planted in that first billion years, and two leading theories point to possible origins from this primordial era. The first theory is a direct legacy of the first stars. When the most massive of the population, 3 stars, ended their lives, their cores collapsed. For stars above a certain mass, this collapse did not result in a supernova that scattered everything. Instead, it left behind a black hole, perhaps tens or even 100 times the mass of the Sun. This stellar mass black hole would then sit at the center of its host minihalo, a ready-made seed. As the protogalaxy grew through mergers and accumulated more gas, this seed would feast, slowly growing over hundreds of millions of years. But for some scientists, this growth seems too slow to explain the most ancient supermassive black holes we observe. This leads to a second, more dramatic possibility: the direct collapse black hole. Imagine one of those vast, pristine clouds of hydrogen gas at the heart of an early dark matter halo, but in a special environment. Perhaps it was in a region where the intense ultraviolet light from a nearby first star prevented the gas from cooling and fragmenting into many stars. Without the ability to fragment, the entire gigantic cloud, weighing perhaps 100,000 solar masses or more, could have become unstable. It would have skipped the star formation phase entirely, collapsing directly into a single, immense black hole seed. This would not be a stellar remnant, but a primordial monster born from a gas cloud, a seed already thousands of times heavier than any star could produce. Once formed, whether from a dead star or a direct collapse, this seed was perfectly positioned. It resided in the deepest part of the protogalaxy's gravitational well, where all the infalling gas and merging structures would naturally funnel toward it. It began a billion-year feast, swallowing gas and sometimes even merging with other black hole seeds when galaxies collided. This relentless consumption is what would eventually power the brilliant quasars we see lighting up the young universe, beacons so fierce they can outshine 1,000 galaxies. The silent seeds planted in the first cosmic towns were destined to become the ruling powers of the galactic cities to come. Those brilliant bubbles of ionized gas were not just local events, they were the opening salvos in a universal war of light against darkness. This is the Epoch of Reionization, the universe's great transformation from a neutral fog back into a transparent, ionized plasma, and it was the defining project of the first stars and galaxies. Remember, after the cosmic microwave background was released, the universe was filled with neutral hydrogen atoms, each one a simple proton and electron bound together. That first starlight, however, was a torrent of high-energy ultraviolet photons. When one of these photons struck a neutral hydrogen atom, it delivered a knockout blow, blasting the electron free and leaving behind a lone, positively charged proton. This process is ionization, and reionization simply means doing it again on a cosmic scale after that initial neutral state. But this was not a sudden, universal flip of a switch. It was a gradual, messy, and patchy process that unfolded over hundreds of millions of years. Think of a dense forest shrouded in a thick morning fog. As the sun rises, the first rays strike the tallest trees, burning off the mist immediately around their peaks. Slowly, these clear patches grow, merging with others, until the entire forest is bathed in sunlight and the fog has completely vanished. That is the story of reionization. Each early star, and later each bustling protogalaxy, acted as one of those tall trees, carving out its own growing bubble of clear, ionized space. For eons, the universe was a cosmic patchwork quilt, with vast neutral voids separating these brilliant, ionized islands. Over time, as more stars ignited and galaxies grew and merged, their bubbles expanded and began to overlap. The frontiers of light pushed further into the darkness, the ionized regions connecting into ever larger clear territories. This great clearing was largely complete by the time the universe was about 1 billion years old. The result was profound. That pervasive sea of neutral hydrogen, which had absorbed certain wavelengths of light for so long, was now a diffuse plasma of free protons and electrons. The universe became transparent again, not to all light, but to the specific ultraviolet and visible light that had been trapped before. This is why we can see galaxies from this era and beyond, their light finally able to travel across the cosmos to our telescopes. Reionization is not just a footnote, it is a major observational frontier today. Astronomers hunt for the faint radio signature of that neutral hydrogen, a whisper from before the fog lifted, and study the most distant quasars to see how their light was filtered by the last remnants of the neutral gas. It marks the final major transition of the infant universe, the moment the cosmic stage was fully set, cleared of its primordial haze, and made ready for the grand, structured drama of galaxies to unfold in plain sight. The fog of the cosmic dark ages may be impenetrable to our eyes, but it is not entirely silent to our instruments. How can we possibly study an era with no light, an epoch defined by its very absence of the very thing our telescopes are built to see? The answer lies in brilliant, indirect detective work, where astronomers piece together the story from subtle whispers and ghostly signatures left behind in the modern cosmos. This is the challenge of probing the first billion years, and it requires not one but multiple ingenious lines of evidence, each a different clue in the same cosmic mystery. The first clue is etched into the oldest light we have, the cosmic microwave background. While its temperature map shows us the infant universe's density, its polarization, the specific direction in which those light waves vibrate, carries a later imprint. As the first starlight began to reionize the universe, scattering free electrons, it left a faint, swirling pattern in this polarization. By carefully measuring this pattern with observatories like the Planck satellite, we can estimate when reionization happened and how vigorous those first sources of light must have been. It is like finding the subtle, blurred reflection of a long-extinct fire in the glass of a very old photograph. A second, and perhaps the most anticipated, clue is a specific radio whisper from the hydrogen gas itself. Neutral hydrogen emits a faint radio signal at a wavelength of 21 centimeters, a signature as fundamental as a fingerprint. During the Dark Ages and reionization, the entire cosmos was filled with this signal. But as the universe expanded, this signal was stretched or redshifted to much longer wavelengths. By building colossal radio telescopes like the Future Square Kilometer Array, astronomers hope to tune into this ancient radio station. They will not hear a continuous tone, but a map of static that changes over cosmic time. By listening to different frequencies, which correspond to different epochs, they can create a three-dimensional movie of the Dark Ages lighting up, watching as the first brilliant bubbles of ionization grow and merge to clear the fog. This would be the most direct portrait of the era we could ever hope to obtain. The third line of attack is to push our sight to its absolute limit, to hunt for the very first luminous objects themselves. We do this by staring deeper into space and thus further back in time with our most powerful infrared telescopes like the James Webb Space Telescope. The light from the earliest galaxies and quasars has been stretched so dramatically by the expansion of the universe that it arrives not as visible light but as infrared. By collecting this incredibly faint, redshifted glow, we can actually see the builders of reionization at work. Each distant smudge of light is a protogalaxy from that foundational era, and by studying their numbers, their brightness, and their spectra, we can understand what kind of stars powered them and how quickly they transformed their surroundings. Together, these methods form a powerful trifecta. The cosmic microwave background gives us the grand timeline. The 21-centimeter signal promises a direct map of the neutral gas, and infrared astronomy shows us the individual actors on the stage. It is a cosmic reconstruction project where each piece of evidence cross-checks and informs the others, slowly pulling back the veil on the universe's most formative and hidden chapter. The story of the first billion years was long a theoretical one, written in equations and simulations. But in recent decades, that story has been given faces, names, and light. Our window into this ancient era has been pried open by a series of remarkable space observatories, beginning with the Hubble Space Telescope and now revolutionized by the James Webb Space Telescope. These instruments do not just take pretty pictures, they are time machines. Their power comes from a fundamental cosmic phenomenon called redshift. As the universe expands, the light traveling across it from distant galaxies gets stretched to longer, redder wavelengths, like the sound of a receding siren dropping in pitch. The more distant the galaxy, the longer its light has traveled, and the more it is stretched. For the earliest galaxies, this stretching is so extreme that their ultraviolet and visible light, emitted as brilliant blue starlight, arrives at our telescopes as infrared radiation, invisible to our eyes. Hubble, with its sensitive instruments, pushed this frontier to incredible distances, spotting galaxies from when the universe was only about 400 million years old. These were blurry, red smudges, but they proved that large structures had assembled with shocking speed after the Big Bang. Then came James Webb, designed specifically to see in the infrared. It is the ultimate time machine, built to catch that stretched starlight from the very first stellar systems. What it has seen is both confirming and confounding. Webb has identified a surprising abundance of bright, well-structured galaxies existing when the cosmos was a mere 200 to 300 million years old. Some of these galaxies appear more massive and more evolved than many theorists expected for such an early time. This is the beautiful tension of science, observation pushing up against prediction, forcing us to refine our models of how dark matter halos gathered gas and how quickly stars could ignite within them. Each faint, redshifted point of light is not just an object, it is a data point in the universe's own biography, telling us that the transition from darkness to a structured cosmos happened with a swiftness and efficiency we are still striving to fully understand. These faint, early galaxies are not the only beacons from that foundational era. There exists another class of object, far rarer but impossibly brilliant, that acts as a cosmic lighthouse piercing the last of the primordial fog. We call them quasars, and their existence so early in cosmic history is one of the most startling clues we have about the first billion years. A quasar is not a star, but the intensely luminous heart of a young galaxy, powered by a supermassive black hole on a cosmic feeding frenzy. Imagine a black hole weighing 1 billion suns, surrounded by a vast, swirling disk of gas and dust. As this material spirals inward, it compresses and heats to millions of degrees, glowing with a ferocious light before vanishing across the event horizon. This process, called accretion, can release a staggering amount of energy, outshining every single star in its host galaxy combined. A single quasar can be brighter than 1 trillion suns, visible across more than 90% of the observable universe. Their name, short for quasi-stellar radio source, comes from the fact that in early images they looked like points of light, indistinguishable from stars. But their spectra revealed the truth. They were moving away from us at tremendous speeds, meaning they were not local stars at all, but the most distant, energetic objects ever detected. The most distant quasars we have found existed when the universe was less than 700 million years old. Think about what that means for a moment. In that short span of cosmic time, not only had the first galaxies assembled, but at the heart of at least some of them, black hole seeds had gorged themselves, growing to masses of over 1 billion suns. This tells us the building blocks of cosmic structure came together with breathtaking efficiency. These quasars are not just record breakers, they are indispensable scientific tools. Their phenomenal brightness makes them perfect flashlights. As their light journeys for billions of years to reach us, it passes through the sparse gas that fills the space between galaxies, the intergalactic medium. Atoms in this gas, like neutral hydrogen, absorb specific wavelengths of that brilliant light. By the time the quasar's spectrum arrives at our telescopes, it is etched with an intricate pattern of dark absorption lines, a cosmic barcode. Each line tells a story. It reveals the composition, temperature, and density of the gas the light passed through. Most importantly, by studying the absorption from neutral hydrogen in the spectra of the most distant quasars, astronomers can map the final stages of reionization. They can see how the last patches of neutral fog were being burned away by the growing light from early galaxies and quasars themselves. So these brilliant monsters, born from the deepest gravitational wells of the infant cosmos, serve a dual purpose. They prove that supermassive black holes grew to immense sizes with shocking speed, and they illuminate the very era of their own birth, allowing us to read the final chapters of the universe's great transformation from darkness into light. The legacy of those first brilliant islands was not isolation but community. As the universe aged past its first billion years, the story of structure shifted from one of birth to one of connection, a grand choreography dictated by the invisible hand of gravity. The dark matter web, that cosmic skeleton laid down in the primordial darkness, began to mature. The subtle density ripples imprinted at the beginning of time were the universe's only blueprint, and gravity was its patient builder. Through a process called gravitational instability, the slightly denser regions within that web experienced a powerful snowball effect. Their extra mass gave them a stronger gravitational pull, which attracted more dark matter and gas from their surroundings. This increased their mass further, strengthening their pull even more. Over hundreds of millions of years, the faint wrinkles in the cosmic fabric deepened into pronounced canyons and towering mountains of invisible mass. The web's filaments grew thicker and more defined, while the nodes where filaments intersected swelled into immense gravitational anchors, and where the dark matter led, the luminous universe followed. Those first protogalaxies, once scattered like lonely outposts, found themselves drawn along these invisible rivers of gravity. They began to stream toward the intersections of the web, gathering together. This is hierarchical clustering, the universe's building principle of assembling small things into ever larger things. Single galaxies merge to form pairs, then small groups of a few dozen galaxies bound together by their mutual gravity. These groups, in turn, were pulled along the dark matter filaments toward the densest nodes, where they assembled into the first, young galaxy clusters, vast cities of hundreds or even thousands of galaxies. You can see the echo of this process in the cosmos today. When astronomers map the positions of millions of galaxies, they don't see a random scatter. They reveal an intricate, frothy architecture, a cosmic web in light. Gigantic, nearly empty voids stretch hundreds of millions of light years across, bordered by dense walls and filaments of galaxies, with immense clusters glowing at the intersections. This breathtaking large-scale structure is not a modern invention. It is the direct result of gravity amplifying those initial quantum whispers over billions of years. The Great Walls we observe, like the Sloan Great Wall, are simply the mature versions of those first dark matter filaments, now decorated with the shining lights of countless descendant galaxies. The universe transformed from a sparse collection of pioneer settlements into a vast, interconnected civilization of light, its map drawn by the dark. This grand web of light and dark is not empty space. The vast voids and filaments between galaxies are filled with an extraordinarily thin gas, the intergalactic medium. While it contains less than 1 atom per cubic meter, this diffuse sea holds a chemical record of the entire cosmic story, a fossilized memory of that first billion years. To read this record, astronomers use the most powerful flashlights in the universe, quasars. As a quasar's brilliant beam travels for billions of years to reach us, it passes through this sparse intergalactic gas. Atoms within the gas absorb very specific wavelengths of that light, leaving behind dark notches in the quasar's spectrum. For neutral hydrogen, the most important absorption line is called Lyman-Alpha. But because the gas is not in one uniform slab but spread in clouds at different distances and moving at different speeds, we don't see one single dark line. Instead, we see a dense forest of hundreds or even thousands of absorption lines, each one a fingerprint from a specific cloud of hydrogen along the line of sight. This is the Lyman-Alpha Forest, and it is a treasure map of the universe's structure. By analyzing this forest in the light of a single quasar, astronomers can reconstruct a detailed, one-dimensional slice of the cosmos, charting where clouds of neutral and ionized hydrogen lie across billions of light years. But the story gets even richer. Those absorption lines are not just from hydrogen. Scattered among them are fainter lines from heavier elements like carbon, oxygen, and silicon. This is the crucial evidence. These metals should not exist in the pristine intergalactic medium, far from any galaxy. Their presence there is the direct signature of those first supernovae from the earliest stars. Those titanic explosions acted as cosmic crop dusters, seeding the void with the first heavy elements. By measuring the strength and distribution of these metal lines in the Lyman-Alpha Forest, scientists can trace how this chemical enrichment spread from the early galactic neighborhoods out into the cosmic countryside. They can watch, in effect, as the universe transitioned from a state of pure simplicity to one of increasing complexity. The forest thus becomes a dual timeline. It maps the progress of reionization, as the once neutral hydrogen clouds were gradually ionized and their absorption changed. And it chronicles the gradual pollution of deep space, the moment the universe went from being a place of only hydrogen and helium to one sprinkled with the raw ingredients for rocky planets and, ultimately, life itself. It is a fossil record written not in stone but in shadow and light, telling the story of how the first stars changed everything, even the emptiness between the galaxies. But how do we test this sweeping narrative against the hard evidence of a few faint, ancient lights? We build a new universe inside a supercomputer. These are not video game graphics, but rigorous digital laboratories where we can run the experiment of cosmic history over and over again, watching our theories succeed or fail. The most ambitious cosmological simulations begin with the only two things we can truly trust: the initial conditions captured in the cosmic microwave background and the fundamental laws of physics. With these as their foundation, they set in motion a virtual cosmos, modeled by billions of particles representing dark matter and gas. The code then calculates, moment by virtual moment, the relentless pull of gravity, the complex hydrodynamics of gas cooling and heating, the explosive feedback from supernova, and even the intricate chemistry that forms molecules like hydrogen. Projects with names like Illustris TNG, Eagle, or the Cosmic Dawn simulations are the engines of this digital creation. They allow us to witness, in a matter of weeks, the entire 13.8 billion-year saga of structure formation unfold before our eyes. We watch dark matter weave its cosmic web, see the first protogalaxies spark to life within it, and observe how stellar radiation and supernova winds carve out bubbles and enrich the virtual intergalactic medium. These simulations are indispensable because they connect the dots between our sparse, precious observations. When the James Webb Space Telescope spots a surprisingly bright galaxy in the early universe, theorists can feed its properties into a simulation and ask what initial conditions could have produced this. Does it require a change in how stars form or a different behavior of dark matter? The simulation becomes a bridge, allowing us to interpret a single blurry snapshot as part of a dynamic, evolving story. They provide a visual narrative for processes no telescope will ever directly see, like the silent collapse of a dark matter minihalo or the merger of two protogalaxies in the pitch black of the Dark Ages. In this way, the digital universe and the observed universe are in constant dialogue, each refining our understanding of that foundational first billion years and the magnificent structures that emerged from the dark. Yet for all the power of our simulations and telescopes, the early universe remains a realm of profound puzzles. The most thrilling moments in science often arrive not when theory perfectly matches observation, but when it does not. These tensions are not failures, they are the universe's way of pointing toward deeper truths we have yet to grasp. The James Webb Space Telescope, our premier time machine, has delivered a stunning surprise. It has found galaxies in the very young cosmos that appear brighter, more massive, and more structurally mature than many leading models predicted. According to some simulations, there simply shouldn't have been enough time for dark matter halos to gather so much gas and forge so many stars so quickly after the Big Bang. It is as if we discovered thriving, complex cities in what our history books described as a sparsely populated wilderness. This discrepancy forces a fascinating reevaluation. Perhaps the first stars formed with even greater efficiency than we thought. Or maybe the early gas clouds collapsed into stars under different physical rules. Some scientists are even exploring whether the nature of dark matter itself might need a slight tweak in these extreme environments. This is how discovery works. Observation pulls theory forward into new and unexpected territory. Another enduring mystery swirls around the very first generation of stars themselves, the population 3 giants. While our models suggest they were colossal, we have never directly observed a single, definitive example. Their initial mass function, the distribution of sizes they were born with, remains a theoretical sketch. Did they form exclusively as behemoths hundreds of times the Sun's mass, or was there a wider range, including some smaller stars that might still be shining faintly in the halos of modern galaxies? The answer is locked in the chemistry of the oldest stars we can find. The search for their pure, metal-free descendants is one of astronomy's great treasure hunts. The Epoch of Reionization, too, holds its own questions. While we know it happened, the precise timeline and the primary architects are still being debated. Was reionization driven mostly by the brilliant light of those massive first stars? Or did the fierce radiation from early supermassive black holes and quasars play the dominant role? Was it a swift and uniform process, or a drawn-out and patchy one that varied dramatically from one region of space to another? The faint radio signal of the 21-centimeter line, if we can finally map it, will tell this story in detail, showing us the exact shape and growth of those first bubbles of light. These are not dead ends, but the most exciting frontiers in cosmology. Each tension between what we predict and what we see is a signpost pointing toward a missing piece of the puzzle. They remind us that the first billion years, though foundational, is not a closed book. It is a dynamic, ongoing investigation where every new observation from telescopes like Webb and every more sophisticated simulation running on the world's most powerful computers brings us closer to understanding how a universe of perfect simplicity became the complex, structured, and luminous cosmos we call home. The mysteries are not a barrier to knowledge, they are the very reason we keep looking up. The potential for life's ingredients stretches back far earlier than we once dared to dream. While the first stars lived and died in brilliant flashes, their explosive legacies created a new possibility within the swirling gas of second-generation star systems, the birth of the very first planets. This is a deeply speculative frontier, yet one grounded in the inevitable physics of a cooling, metal-enriched universe. When a massive first star ended its life in a pair-instability supernova, it did more than just scatter heavy elements into the void. It fundamentally changed the properties of the cosmic gas. That enriched material, now seeded with elements like silicon, carbon, and iron, could cool far more efficiently. As this next wave of gas collapsed to form smaller, longer-lived stars, it naturally conserved its rotational spin, flattening into vast, swirling disks of dust and gas around the newborn stars, what we call protoplanetary disks. We see this process unfold around young stars in our own galactic neighborhood today, the clear nurseries for new planetary systems. So, if the physics is the same and the necessary metals were present, then the formation of planets could have begun almost immediately after the first generation of stars completed its work. This leads to a staggering thought. Within just a few 100 million years of the Big Bang, while the universe was still clearing the final patches of its primordial fog, the very first rocky worlds could have been taking shape in orbit around small, stable stars. These planets would have been forged from the ashes of the very first stellar giants, their cores rich with iron and their crusts potentially sprinkled with silicates and even water ice delivered by cometary material. The cosmic timeline for habitable environments, once thought to begin many billions of years later, may need to be rewritten to start in that astonishingly ancient era. While we have no direct evidence of such primordial planets yet, their possible existence challenges our understanding of life's potential window in the cosmos, suggesting that the stage for biological complexity may have been set in the universe's first fleeting chapters. By the time the universe celebrated its first billionth birthday, the transformation was absolute. The long, silent dark ages were a fading memory, replaced by a cosmos alive with structure and light. At this milestone, corresponding to what astronomers call redshift 5 or 6, the universe we would recognize was firmly in place. The pervasive sea of neutral hydrogen that once absorbed starlight was now almost completely ionized, a diffuse, transparent plasma that allowed light to travel freely across vast distances. This great clearing of the cosmic fog meant the stage was finally set, unobstructed, for the grand drama of galaxies to play out in full view. Look out across this young cosmos, and you would see not just a few scattered points of light, but a growing tapestry. Galaxies of various shapes and sizes glittered everywhere, no longer isolated pioneer settlements but thriving communities. They were drawn into clusters and long, luminous chains that traced the invisible filaments of the dark matter web, a brilliant embroidery on the cosmic skeleton. In the densest nodes, the first great galaxy clusters were taking shape, gravitational anchors for everything to come. The intergalactic medium, once pristine, now carried a faint but detectable trace of heavy elements: carbon, oxygen, silicon, the indelible pollution from billions of supernovae that had already lived and died. The universe was no longer simple, it was chemically enriched and complex. The foundational work was done. The quantum seeds planted in the first instant had grown through gravity's patient pull into a vast, interconnected architecture. The cycle of star birth, life, an explosive death was established, steadily forging new elements and scattering them into future stellar nurseries. With the basic rules set and the universal landscape defined, the cosmos transitioned from its era of frantic, foundational construction into a new phase of refinement and evolution. The next 12 billion years would be a story of maturity, of galaxies merging, growing, and settling into the majestic forms we see in our night sky today. The first, most daring chapter was complete, leaving behind a universe ready to build upon its own astonishing beginnings. This cosmic legacy is not a distant abstraction. It is written into the very fabric of our being. Every atom in your body heavier than hydrogen or helium carries the echo of those first stellar furnaces. The iron in your blood that carries oxygen, the calcium in your bones that gives you structure, and the carbon that forms the backbone of your DNA. All of these were forged in the hearts of massive stars that lived and died billions of years before our sun even ignited. Their spectacular supernova deaths were not an end, but a scattering, a sowing of elemental seeds across the galactic plains. Those seeds drifted for eons, eventually mixing into the vast cloud of gas and dust that would collapse to form our solar system some 4.6 billion years ago. You are literally made of stardust, the processed and recycled remains of ancient giants from the universe's first chapters. But the connection runs deeper than chemistry. The grand architecture born in that first billion years also dictated our cosmic address. The subtle gravitational pull of the primordial dark matter web guided where the great clusters and filaments would form, and where the vast, quiet voids would stretch. Our Milky Way galaxy did not form in a random location. It took shape along one of those rich filaments, in a relatively quiet suburban neighborhood of the cosmic web, far from the chaotic core of a massive cluster. This specific placement was crucial. A galaxy in the dense, violent heart of a cluster might be stripped of its gas too quickly or experience too many disruptive collisions, potentially hindering the long, stable evolution needed for complex life to arise on a rocky planet. The universe's first decisions, imprinted as quantum ripples and amplified by dark matter, ultimately set the stage for a spiral galaxy to form in a stable region, for a star like our Sun to be born, and for a planet like Earth to coalesce from that enriched stardust. When you look up at the night sky, you are not just looking out into space, you are looking back at your own origin story. The ancient light from distant galaxies and the silent pull of the dark web are part of the inheritance that made your existence possible. The universe built itself from simplicity to complexity, and we are one of its most intricate and recent results, a living testament to that foundational era of darkness, fire, and structure. Yet our view into this dawn remains fragmented, a handful of whispers against the cosmic silence. To truly hear the story of the first stars and galaxies, we need a new generation of listeners, instruments designed not just to see deeper, but to hear the universe in wavelengths it has been humming all along. The coming decade will be defined by a suite of revolutionary observatories, each one a specialist trained to decode a different part of this ancient signal. First, the Nancy Grace Roman Space Telescope, set to launch in the late 2020s. Think of Roman as a cosmic surveyor with a phenomenally wide-angle lens. While the James Webb Space Telescope is a powerful magnifying glass staring at tiny, deep patches of sky, Roman will take sweeping panoramic portraits. Its primary mission is to study dark energy and exoplanets, but its immense field of view is perfectly suited for a different kind of hunt, catching the flash of the very first stellar deaths. Remember those pair instability supernova from the massive population 3 stars. They are predicted to be extraordinarily bright and to fade in a very specific, slow manner. Roman will scan huge volumes of the early universe, essentially monitoring billions of galaxies at once, waiting for these characteristic flashes to appear and then vanish. It is like setting up a network of security cameras across a vast wilderness, hoping to finally capture footage of a creature we have only ever seen in fossilized footprints. If successful, Roman will not just infer the existence of the first stars, it will give us a direct statistical census of their explosive deaths, telling us how common these giants truly were. Meanwhile, on the ground, a project of staggering scale is taking shape, the Square Kilometre Array, or SKA. This is not a single telescope, but a vast network of radio antennae spread across South Africa and Australia, forming a collecting area of, as the name suggests, a square kilometre. Its prime target is the most elusive whisper of all, the 21-centimetre signal from neutral hydrogen during the cosmic dark ages and reionization. The SKA will attempt to tune into this ancient radio station, not for a single note, but to create a three-dimensional map of the early universe's structure. By listening to different frequencies which correspond to different cosmic times, it will produce a movie showing the neutral hydrogen fog as it first gathers into filaments and then is gradually burned away by the growing bubbles of light from the first galaxies. This map would be our most direct view of the Dark Ages, a sonogram of the cosmic web in its infancy, and the James Webb Space Telescope is far from finished. Its future observation cycles are already planned to push even further back in time, hunting for the chemical fingerprints of population 3 stars within the earliest galaxies. While finding a single, pure first-generation star may remain elusive, Webb might spot entire small star clusters whose combined light shows a severe lack of heavy elements, the unmistakable signature of a stellar nursery still working with the universe's original recipe. Together, these missions form a coordinated assault on the frontier. Roman will catch the brilliant final moments, the SKA will map the silent scaffolding, and Webb will analyze the chemical legacy. They promise to transform our understanding from a compelling theoretical sketch into a detailed, observational history, finally bringing the universe's first and most formative chapter into sharp, undeniable focus. Studying this ancient dawn is not merely an academic exercise in cosmic history. It is a direct investigation into our own deepest origins. Every question we ask about that first billion years is a question about how existence itself transitioned from perfect simplicity to the rich complexity we see today. We are searching for the initial conditions that set the entire cosmic story in motion. By understanding how the first luminous objects ignited, we learn the fundamental rules governing how gravity assembles matter and how radiation transforms its surroundings. This era acts as a unique laboratory, testing the laws of physics under the most extreme environments the universe has ever produced, conditions of density, temperature, and energy we could never hope to recreate on Earth. The behavior of dark matter, the formation of the first black holes, the nucleosynthesis of the first heavy elements, all of these processes are written into the fabric of that formative time. When we detect the faint light of an early galaxy or map the whisper of primordial hydrogen, we are not just collecting data about distant objects, we are reading the opening lines of our own cosmic biography. This research addresses the profound human curiosity about where we come from and how our place in the universe became possible. It traces the lineage of the iron in our blood and the calcium in our bones directly back to the furnaces of those first massive stars. It explains why we find ourselves in a spiral galaxy, nestled along a filament of the cosmic web, rather than adrift in a vast void or trapped in a chaotic cluster core. The decisions made in that first billion years, dictated by quantum fluctuations and dark matter, ultimately crafted the specific cosmic stage upon which life on Earth could eventually emerge. To study this era is to piece together the very first chapter of a story that leads 13.8 billion years later to us looking up at the night sky and wondering how it all began. The answers we seek are not just about the past, They are about understanding the fundamental architecture of reality and our own intimate connection to the grand tapestry of the cosmos. The entire cosmos we see today, from the grandest galaxy cluster to the smallest grain of stardust, traces its lineage back to a single, unified origin story. This is the narrative of cosmic dawn, the epic transition from simplicity to structure, a chain of events so interconnected that each step made the next one possible. It began with the faintest of quantum whispers, microscopic ripples in the newborn fabric of space-time that was stretched to cosmic proportions during inflation. These became the primordial density fluctuations, the only blueprint the universe would ever receive. While ordinary matter remained trapped in a hot, radiant fog, dark matter began responding to the gravitational pull of those overdensities first, quietly weaving the vast, invisible skeleton of the cosmic web. Within the deepest gravitational wells of this dark matter scaffolding, the first clouds of pristine hydrogen and helium gathered. Their collapse required a fragile coolant, molecular hydrogen, which allowed the densest cores to shed heat and continue falling inward. This set the stage for the ignition of the first stars, the colossal population three giants, whose searing ultraviolet light pierced the universal darkness and began carving the first bubbles of ionized space around them. Their brilliant, brief lives ended in spectacular supernova, performing the universe's first act of alchemy by forging heavy elements and scattering them into the void. This chemical enrichment forever changed the cosmic recipe, allowing future gas clouds to cool efficiently and fragment into the smaller, longer-lived stars we know today. Gravity then drew these first stars and their enriched gas into the first protogalaxies, stable islands within the dark matter halos. At the hearts of some of these early systems, black hole seeds took root, either from the collapsed cores of the most massive first stars or from the direct collapse of immense gas clouds, planting the future power sources for brilliant quasars. The collective light from these growing galaxies and quasars then undertook the universe's great transformation, the Epoch of Reionization, where bubbles of ionized gas expanded and merged over hundreds of millions of years until they cleared the cosmic fog entirely, rendering the universe transparent. By the end of that first billion years, the work was complete. The dark matter web was now traced in light, decorated with galaxies arranged in clusters and filaments. The intergalactic medium was subtly enriched with the elements for future planets. The stage was fully set. This entire saga, from quantum seed to luminous cosmos, is not a series of isolated events, but a single, magnificent cascade where gravity, light, and nuclear fusion worked in concert. Each chapter was written by the one before it, building a universe of breathtaking complexity from the humblest, most silent beginnings. The first billion years were a symphony of transformation, where every movement relied on the one before it. From silent quantum ripples to a structured cosmos ablaze with light, this foundational era established every rule, every pattern, and every potential for the universe we inhabit today. It was a period of dramatic transition that set the cosmic stage for the next 12 billion years of galactic evolution, stellar life cycles, and ultimately, the emergence of worlds like our own. Humanity's achievement in deciphering this story is itself a wonder. From the faint, redshifted glimmers captured by our greatest telescopes to the intricate digital universes born in supercomputers, we have learned to read the universe's memoir written in light, shadow, and theoretical elegance. We have connected the dots between the afterglow of creation and the iron in our blood, weaving a coherent narrative from fragments of evidence across the vastness of space and time. Yet for all we have uncovered, profound mysteries persist. The true nature of the dark matter that sculpted the cosmic web remains elusive. The exact properties of those first, gargantuan stars are still hidden in the observational static. The detailed timeline of reionization awaits its final map, Each unanswered question is not an end but an invitation, a reason to keep looking, to keep listening, and to keep building the next generation of tools that will peer even deeper into the dawn. As new data streams in from observatories like the James Webb Space Telescope, and as future projects like the Square Kilometer Array come online, this story will be refined, challenged, and rewritten. The cosmic dawn is an ongoing investigation, and we are all witnesses to its unfolding. To continue exploring the building blocks of this grand narrative, you might delve into the enduring enigma of dark matter or the latest revelations from the frontier of infrared astronomy. The universe's first chapter has been opened, and the next pages promise revelations just as astonishing.